Hi, everyone. Welcome back to our oral presentation. Then let me introduce our third presenter. So Maria Tariq is a second-year PhD student. She's currently pursuing her degree from the Center for Computational Science and Mathematical Modeling at Coventry University. So today, she's going to talk about her conference paper, Transfer Learning-Based Classification of Diabetes Retin Perfect on Cargo IPEX dataset. She has extensively analyzed the challenge of the largest available dataset, Cargo IPEX. Through her work, you will learn about deep pre-trained models, multi-class classification, and transfer learning. Now let's welcome Maria.
Hello everyone, my name is Maya Tariq and I'm doing PhD at Coventry University in the Center for Computational Sciences and Mathematical Modeling. The title of my conference paper is Transfer Learning-Based Classification of Diabetic Retinopathy on Kegel IPEX Dataset. So from the title, you can see I'm working on a medical problem, diabetic retinopathy. It is an eye complication and it is the consequence of advanced stages of diabetes. So I'm working on eye. So from a normal person's point of view, you can understand only this image, but behind this image, we have a detailed view of eye and only a medical expert can understand this one. This is the image I am working on and this is after screening. So diabetes has two types, type 1 and type 2. According to London School of Hygiene and Tropical Medicine, 54.6% of people with type 1 diabetes and 30% of people with type 2 diabetes can have diabetic retinopathy. There are certain risk factors involved in worsening this disease: high blood pressure, high sugar levels, high cholesterol level, and duration of diabetes. So we need to work on these factors to avoid diabetic retinopathy. Okay, you can see two images here. On the left side, you can see a normal person's vision, whereas on the right side, you can see the vision of diabetic retinopathy person. You cannot see colors, you cannot see details in the image, and a person can only have a blurry image, and he can even get blind in this disease. So there are two images. One is related to healthy retinal image and the other is diabetic retinopathy image. In healthy retinal image, you can only see optic disc, macula, and some normal blood vessels. Whereas on diabetic retinopathy side, you have different small lesions of diabetic retinopathy. And these lesions start appearing continuously with each stage of diabetic retinopathy. And there is certain risk factor involved in this one because a doctor can only understand this one, but he can also get mistaken in this one. So according to our research, 2.6 million of world population were visually disabled in 2015, and it was then predicted to increase to 3.2 million people in 2030. And it is also predicted to increase to 191 million people by 2030, which is a very huge number. There is no cure of this disease. It can only be controlled. And only two things we can do: early detection and proper treatment can decrease the risk of permanent visual loss up to 60%. So, and also there is also a risk factor, human risk factor involved in this one. So we need an automatic approach, a quantitative approach to help the medical staff to examine the severity of this disease. In this paper, we have done an extensive study on Kegel IPEX dataset. That is the largest available DR dataset that is publicly available, and using pre-trained models ResNet 50 and DenseNet 121. This paper has highlighted the conflicted classes within the dataset and certain challenges of IPEX dataset. such as noise, incorrect labeling, and imbalanced classes during classification. We have introduced a combination of different image pre-processing techniques and hyperparameter techniques to improve the model's performance. Aptos dataset is used in comparison with the IPEX dataset to investigate the performance of our model. So this is the dataset we have used, Kaggle IPEX dataset. This dataset has quite a lot of challenges, but it has 35,000 images that are annotated for training. It has 5 classes, and you can see that the classes are imbalanced, and you can also see some of the sample images for each class. So the first step is the data collection, which we have got from the Kaggle repository. Then we have used image pre-processing techniques and basically cropping and resizing according to our models. And the models we have used ResNet 50 and DenseNet 121. So you can see the architecture of the models. For ResNet 50, we have used 224 by 224 image resolution, and it has identity blocks. And on the other hand, in DenseNet, we have done experiment using both the resolutions 224 by 224 and 512 by 512, and it has a concept of dense blocks. So we have also done fine tuning with hyperparameter techniques, and these are the hyperparameter techniques we have used. For loss function, we have used sparse categorical focal loss. It works better when you have imbalanced classes and small details to learn in the images. And then in early stopping, the metric we have used is validation accuracy. Then we have used Adam optimizer, and the learning rate on which our model performed well is 0.001. For the model layers, we have frozen the initial layers of the model, and the last few layers are trained to extract informative features from the images. Then we have done analysis of conflict classes, comparison with SVM, and we have done filtration on class 0 through clustering. So these are the results where we have done the analysis of conflict classes. In these experiments, we can see that class 0 has conflict with class 1 and class 2. And for what I'm saying when I'm saying that conflict classes, it means that the accuracy of one class increased, then the accuracy of the other class decreased. And when the accuracy of the first class decreased, the accuracy of the other class increased. It's like a seesaw problem. So we have seen the same relation between class 0 and class 1, and class 1 and class 2. So we have also done an experiment by combining the 3 classes, the initial 3 classes, which have got conflict with each other in one class, and the sphere classes 3 and 4 on one side to see the result. And it is binary classification, so we have got 99% accuracy on this one. So from these results, the conflict experiment, so there is a question mark that puts in front of the reliability of this data set. And when we talk about comparison with SVMs, so SVM is a non-parametric algorithm which gives the upper estimation of the model's performance. So we have got 52.57 accuracy on SVM, where we have in our model, DenseNet 121, our accuracy got stuck at 48% on 5-class classification. And to check our model's performance or the reliability of our model, we have checked it on our Aptos dataset that is considered to be good quality dataset, but it is very small. So we have got 93% accuracy on this one. Then we have applied k-means clustering on class 0 to see the impact of class 0 on the other classes. So we have chose this class because class 0 is the majority class, and we want to separate some informative images from this class. So in cluster 2, we have got 70% accuracy on with using the same model, and the F1 score for all the individual classes is also good. So you can also see some of the sample images from all the clusters here. So in future, we'll work out on having more quality images from real life hospital data set. And in this case, we are collaborating with NHS. And we have got more than 200,000 images of diabetic retinopathy with correct annotations. And we'll also work on generating high resolution synthetic images for each grade of diabetic retinopathy using GANs to increase the data set for minority classes. And we also want to reduce the need of having more images in the classes. So that's why we're gonna use GANs, and then we'll have our own data set. Thank you.
Thank you for the presentation. Do you have any questions to Maria?
Yes.
Maria, thank you. It was a wonderful presentation.
you.
On the television topic, I was working with the Google Health project and basically developed the diabetic retinopathy system and deployed it into various workplaces in Thailand. And they were mentioning something interesting regarding these data sets. And for example, regarding the high-risk population represented in there, these are already patients that underwent a laser operation. And their systems were actually showing a very high false positive rate on these patients. Did you work with these kind of information, for example, for selection of the data set, or for example, using outer distribution model or something like that? This could be a very interesting approach to apply before actually deploying to clinical practice. Thank you.
Yeah, thank you so much. Actually, I haven't tried like using these type of approaches, but I have used deep learning approaches mostly to see. But the challenge we have faced with this data set is like it has got imbalanced classes, and it doesn't have any quality images. So we are working on this one, but I think the data set problem is quite a big one, and I think everybody is facing this one when you are working in especially the medical field or on the medical problem. So we are also like facing this kind of problems, but I'll surely like focus on what you have just suggested, but I haven't tried this one. Yeah, thank you so much.
Thank you. Any questions? Yes, please.
Do you have a sense of what the various, populations kind of making a prediction on any of these classes is affecting the population? So like, I guess, how confident are we?
Okay, so actually, in the case of diabetic retinopathy, it's like for this data set specifically, what they do is they use the expert opinion of at least three expert opinions, and then they take the majority one. So for this data set, they have done this. So that's why we are having the problem in this data set. But I think usually in the medical field, what they do is they take the majority one, and they make their data annotated by just 2 or 3 experts. So we cannot rely on this one. So we'll have, I think, these problems maybe in future too. So that's why we want to work on the GANs one, so that we'll have our own data set, and on that we can be confident about that. Yeah.
Thank you. That's good.
Thank you so much.
Oh, thank you. Okay. Let me introduce the fourth presenter. Brian holds a degree from University of Stanford, where she graduated in 2019. She is currently a PhD candidate in medical engineering at IKEEP Laboratory, University of Stanford. Brian also holds an engineer position at Zimmer Robotics in France. Her research interests are in non-invasive navigation for knee surgery. In particular, she investigates real-time 3D to 3D registration and point cloud signatures for bone shapes. So Brian will present the paper titled 3D to 3D rigid registration, a comparative analysis starts on thermal bond scans.
Please, Jenny, can you allow me to share my screen?
Okay, so I have to stop mine. Yeah.